Hello, welcome to another problem session. Again, this is from a website, this website which I maintain. And if you have a question, you can let me know through that website. Okay, so what is it is we study here difference between elastic, perfectly elastic and perfectly inelastic collision in just one-dimensional situation. Okay, so if you look at A is about perfectly elastic, and B is about perfectly inelastic. Okay, so we should call it perfectly elastic. Sometimes when we say elastic, we mean it's perfect. And this is when things stick together, we sometimes call it perfectly inelastic. Even if two balls collide, they may be not elastic. Okay, whether they stick or not, they may not be elastic, because sometimes when the ball collide and start to vibrate, and some energy is lost in the internal vibration energy of the balls. So by elastic collision, perfectly elastic collision, what we mean is kinetic energy total before the collision equals kinetic energy total after the collisions. That's what we mean by perfectly elastic. Yeah. So in all collisions, so this circle further, in all collisions, total momentum before equals to total momentum total after. Okay, this is a vector equation. So there will be one along the x-axis, one along the y-axis, one along the z-axis, and this is scalar, meaning one equation, and this is potentially three equations you can get out of this. Okay. But in our case, they're moving the same direction, right? The balls before the collision, they're moving in the same direction, and they're going to collide and collide head-on, meaning the head-on means the direction of motion will not change. So if they're going along the x-axis, they will continue in the x-axis to be oriented along the x-axis. So if I draw a picture here, so this is the before, this is A has a faster velocity, and then B is bigger mass. Draw a bigger picture, smaller, so this is the B and this is the A. This is before situation. This will catch up onto that, and somewhere here A and B will interact. This is at the moment of collision. And over here, because the momentum, total momentum is that way, they will continue to move in that direction. Maybe this has an So they separated out maybe. So this is the after, at, and this is after. So total momentum here will be equal to total momentum there. Total kinetic here will be total kinetic here in a case of A. So this is the situation in A. And situation in B is the same thing. Before is the same. Before is the same. It looks like the same, but somehow they get stuck here. This is at. So, and then after they move together, meaning that they have the same together, same speed. Here they can have different speeds, so it's like a V, VB, and VA. Let's go prime afterwards, and this is VA and VB before. Okay, so because it's one dimension, we can put a x here. So in this case, we are going to have two equations. So we're going to have a momentum conservation and we are going to have a kinetic energy conservation. So every direction is positive here. This one we don't know if it's this way or this way. We don't know if it's going this way, but the net is that way. So we don't know. Maybe one of them definitely has to be that way, and you can't from this picture you can see best to VP prime that way. So momentum is going to be all of them. We don't know, so we can just call it X and call it X. We don't know the direction of it. So this one is plus and this one is plus, right? And I'm going to just use the numerical value because it's easier to do it. So let's, because we need after, so P total X after equals to P total X before, and so the after is going to be 0.2 and for A I have a V AX prime plus 0.4 VBX prime. That's equal to the before is going to be 0.2 and this is going to be plus, this is going to be plus, and this is going to be plus because my axis is this way and these guys are this way, both that. So 10 times 0.2 0.2 times 10 plus 0.4 times 10 8. So this is 2 plus 3.2 is 5.2. Make sure I didn't do any mistake here, didn't make any mistake. 0.2 times 10 is 2. 0.4 times 8 is 3.2. And so 2 plus 3.2 is 5.2. So if I simplify, divide by 0.2 everywhere, so Vx prime plus 2 VBx prime equals to, divide by 0.2, so 52, this becomes 26. So this is equation 1, and 2 is kinetic energy after equals to kinetic energy before, and that's going to give me half times 0.2. Now there is no if you speed goes here, so if you this one has a speed. If you look at the speed is equal to square root of vx square plus vy square plus vz square, and these are 0 here, so this is going to be just vx, right? So I'll just say vax square plus half times 0.4 times vx square, and half times 0.2 times 10 square plus half times 0.4 times 10 square. Okay, so in interest of time, let me calculate and come back to you, simplify it. So I've got these two equations, 1 and 2, and these 1 and 2 I need to solve them simultaneously. Solve 1 and 2 simultaneously. Okay, if I solve them simultaneously, we are going to you can have several strategies. This is not linear equations, so can be done by process eliminations. We can say v a x prime equals 26 minus 2 v x prime, and I can try to plug in here and simplify. So you're gonna get the equation. Okay, so I did the calculation to save time in the video. So let me walk you through the calculation. So I solved the one for VA prime and plugged in here, and I simplified all the way here, and then I put the right side here, and then this I put it over here to further simplification. And this is a quadratic equation, so this is like ax squared plus bx plus c equal to 0 equation. When I do it, I get two answers. So I get this plus or minus this, and so there's this answer and this answer. And then I try to put into this. So if it's 9.4, then I'll get this. And if the B has 8, then it's 10. So you can actually recognize this is the before the collision, and this is the situation after the collision, this pair. So the answer is VA. So after is VA is 7.2 meter per second, and VB is 9.4 meter per second. So this is elastic. Okay, let's go to the inelastic case here. Now here there's only one V. Here I got two different V's, right? But here I'll get a single V. And here before we had this equation, we had conservation of kinetic energy, but here kinetic energy not conserved. So that's important difference. Okay, so when I work it out, only momentum is conserved. So so in this case only this is what will happen. Okay, so from when I apply momentum total, before the collision I have the same. So I've got 0.2, let's call it V prime. v prime plus 0.4, same v prime, this is same vx prime, and that's equal to so this is along the x direction. This is equal to the before the collision is the same, so I just have to copy that 5.2. So common vx prime is just 5.2 divided by 0.6, so 0.3, 2.6, and so 26 over 3 meter per second. I can just simplify more, 8.7 meter per second. So this, both of them have the, so your answer will be VA equals VB equals 8.7 meter per second. Okay, just to recap before we leave this problem is when you have elastic collision, you have two things happening: momentum conservation and kinetic energy conservation, and you have to set up the equation accordingly. Momentum conservation is a vector equation, so it's like a vector equation, and kinetic energy is a scalar equation. So this is going to be one equation, and this can be 2, 3, and 4. So potentially you can have that many equations. All right. And potentially 4 equations, but here, because there's only one direction, we only have 2 equations, and we just go ahead and solve it, and automatically results when we solve it is quadratic, and automatically results in 2 answers, this pair or this pair of the final velocities. And this was the before the collision, it's after the collision. When you have inelastic, then you do not have kinetic conservation, so only momentum conserved. Okay, there is a shortcut to the whole thing, and you may have to remember, in case of elastic collision in one dimension, you can show all of this calculation that took place. You can show, let me take another slide just for a couple of minutes. So elastic collision in one dimension shortcut. So you have a momentum conservation, total momentum, x conserved. So that's one equation, and relative velocity after equals to relative, so this is all along the x direction, relative velocity before. So this does not lead to a quadratic equation. So this one would have led to our equation 0.2 VAX prime plus 2VBX prime equals to 26. So as before, and then this one would have been, if I look at VBX prime minus VAX prime, so that's the relative of B with respect to A, will be same as the relative of VX minus VAX. And in the problem I just forgot to put an absolute value sign here, because in absolute value they're equal, this is coming from kinetic energy conservation equation. It leads to 2 here, and so you can see I can get, this has 2 possibility, VBX prime minus VAX prime equals to plus 2. So this is equation 1, and so this is 2A, 2, maybe 2, just 2, and VBX prime minus VAX prime equals to minus 2. So this is like a 3. And so we solve this, and it's now very easy to solve, right? Just add, and you have a 3 VBX prime equals to 26 plus 2 is 28. So VBX prime is 28 over 3, and 9.3. And if I have this, when you add, you're gonna get VB. So with this will be VBX prime, 3 VBAB, add them again, and it's gonna be 24. And so VBX prime equals to 8. So this one is corresponds to the pair you started, you know, VBX prime equals to 8 and VAX prime equals to 10. So this is the same as before collision. And this one give you VAX prime is put a 9.3 over there, and you're going to get 26 is a 2 here, and 7.3 from here, meter per second. So this is the after the collision. Now this one is much easier to follow, except that you have to really remember that you got to work out these 2 cases, you know, and then you're going to decide, right? So in this case, you absolute relative velocity is before and after equal, and you can prove this from using the kinetic energy conservation, which I'm not going to do, but many people memorize this, and it's really a shortcut if you remember. And if you don't remember, you can always go back and do the kinetic energy conservation, and that should help you a lot. Okay, bye.